Good morning, good afternoon, or good evening, wherever you are. Thank you for attending today's webinar. I am Hero Gulani, soil scientist with USDA ARS, the US lead for the Cropland Research Group and co-lead for the GRA Cropland Research Group with Doctors Rosa Mosquera and Ladiziana Martin. It's my pleasure to introduce our speakers today, Dr. Craig Drury and Diego Abolos. With that, I think we will be starting with the presentation, and then we will have a break at the end for questions. Please put all your questions in the Q&A, and we will be answering as time permits. Thank you. Our first speaker is Dr. Craig Drury, is a soil biochemist with Agriculture and Agri-Food Canada at the Haro Research and Development Center in Southwestern Ontario. He obtained his BS and MS from McGill University and his PhD in soil science from University of Guelph. Craig's primary research focus is to develop soil and crop management practice to reduce ammonia volatilization and nitrous oxide emission from agricultural soil while enhancing soil health and crop yields. Craig is the national lead for the reactive nitrogen indicator in Canada. He is the Canadian representative on the Cropland Research Group and the Conservation and Nitrogen Management Network lead. Craig is a fellow and a past president of Canadian Society of Soil Science. He has served as editor for Canadian Journal of Soil Science, also serving on editorial board of Agriculture, Ecosystem and Environment. And he is currently associate editor of the Soil Science Society of America Journal. With that, I'll turn it over to you, Craig, please. Its floor is yours.
Okay. Can you see my screen?
Yes.
And can you hear me? So you see the first slide then, right?
Correct.
Okay, good.
Thank you.
Yeah, so I appreciate this opportunity to present some of the work that we've been doing, both within the GRA and with sort of the modeling and field studies that have been going on for the last, well, couple of decades, to be honest. So the title that we have chosen here is really one that's near and dear to my heart. It's one where we're working with the Croplands Research Group and the network. There were two networks for a while. One was looking at conservation agriculture practice, and the second, nutrient management. So it looked like there was an opportunity to merge those two networks and try to look at it on a more holistic approach. So the title of the presentation that we're giving is Stacking 4R Practices with Conservation Agriculture to Mitigate Nitrous Oxide and Ammonia Emissions. And the reason why we're adding ammonium is just this whole pollution swapping. We have to be mindful that if we're going to reduce ammonium, that we're not increasing N2O, and similarly, if we're reducing N2O, we're not enhancing ammonia emissions. So let me just proceed with the next slide. Okay. There we go. And again, thank you for the introduction. Diego is going to follow with discussion of some of the meta-analysis that we've been involved with. So first of all, I have to give acknowledgement to the many collaborators who've worked on these studies, both within the GRA and also within our respective research institutes. I have many collaborators within Agriculture and Agri-Food Canada, including Ward Smith, who's a modeler, and multiple other colleagues. Alex Woodley, a former postdoc who's now at the University of North Carolina, with Matt Helmers, Mark Liebig, Jane Johnson, and with also Diego and the colleagues from Aarhus University. So the objectives really are threefold. First of all, is to develop nutrient management strategies, which of course not only reduce fertilizer losses, whether they are N2O emissions, ammonium volatilization, nitrate leaching, but also looking at practices can also enhance crop yields. Achieving both is more likely to get farmer adoption and acceptance of these practices. Canada in particular has set a goal of reducing nitrous oxide emissions from fertilizer by 30% by 2030. And ultimately, we want to look at systems that can achieve net zero emissions by 2050. Now, when I'm talking to producers, I often show this one slide, and it really is everybody who's working on nitrogen has their own versions, happens to be the one that I've used. And the one thing I want to point out here is that there's many biological and chemical processes occurring. You add fertilizer to the soil. If it's on the surface in particular, you can have a lot of ammonia volatilization, especially if the pH goes up. And we can have significant losses of that. If whatever ammonium is left in the soil, if we have a heavy rainfall before the crops utilize the nitrogen, we also see a nitrification going on, conversion of ammonium to nitrate. And if we have a heavy rainfall, especially on heavier textured clay soils, clay loam soils, we can also see N2O emissions and N2 loss. We've also noticed, especially in the fall and over winter periods, significant nitrate leaching occurring through the groundwater, or even to the left of the screen through tile drains. Not so much in surface runoff, but again, it has to be accounted for. Now, when I show this to farmers, of course, they glaze over as we all do. And so the idea was, how can we better represent that process? And I'll be discussing that in a little minute, or a couple minutes, when I talk about the pipe and valve concept model. In the meantime, there was another meta-analysis that was conducted back in 2022. And I just want to highlight the top of these graphs from this paper. So if you look at the top left yield graph, it's the influence of either UI, which is a urease inhibitor, NI, which is a nitrification inhibitor, or the UI-NI is the dual inhibitor. We see that all of these inhibitors can, in fact, increase yields. I flagged the dual inhibitor because it can achieve multiple benefits. We have it on average across all these studies, 3% yield increase. In some regions where I am, I often see more like a 10% or higher yield increase. Ammonium volatilization, again, we see about a 38% decrease in ammonium loss with the dual inhibitor. However, what's noteworthy is if you just use a nitrification inhibitor alone across all these studies, there tends to be an increase in ammonium loss. So that's one of the reasons why we prefer the dual inhibitor. And similarly with N2O emissions, we see a 31% decrease across all these studies. Within Canada, again, we want to look at this as a holistic process. A number of us are involved in environmental indicators, and nitrogen is one of them. We used to really focus on just sort of the nitrate leaching, but more recently been looking at ammonium volatilization losses, as well as N2O emissions. And the key here is that they all represent a loss of nitrogen in the system. So we can not only look at the individual loss mechanisms, but we can also look at it on a national basis using our models. This is all modeling work based upon census data, crop yields across regions, soil types, and so forth, as well as environmental factors, whether it's temperature, rainfall, and so forth. So we've come up with this model, and we can look at it holistically by putting them all together as reactive N. So we see quite a difference across the ag regions within Canada. In the West Coast, there's a lot more rain, so there's more opportunity for higher yields, but unfortunately higher losses, particularly nitrate leaching, some ammonium volatilization into emissions as well. In the center of the country, we have the dryland prairie areas, generally not as high input, certainly doesn't get as saturated, so there's less leaching loss, less N2O emissions. And then Eastern Canada, where I am, which is sort of the southernmost area in Canada, which is just north of Lake Erie, we see that in these regions, very high losses occur, both with nitrous oxide on the upper right, nitrate leaching the left, and also with ammonium volatilization. So we want to be mindful that we're looking at all loss mechanisms. And in fact, these have changed. We've done with the census data and the modeling, we've seen that this was a look at the reactive N loss back in 1981, this large green area, which is a low risk area across all the prairies, and how now the northern, slightly wetter areas are now in a higher risk area. And the higher risk areas increased in Eastern Canada and Western Canada as well. So getting back to that, initial diagram showing all the different losses, when I talk to farming groups, try to do a more conceptual way of describing these losses. So we just published this recently in the Field Crops Research, came out earlier this year. And so here, if we look at the model, here is, as an example, urea being added to these pipes. And it basically is an extension of the Firestone and Davidson hole in the pipe model. But now we're including both ammonium loss, and you'll see in a minute how valves or practices, management practices, come into play. So initially, when urea is added to the soil, first process is urea hydrolysis. If the nitrogen is on the surface or has access to the surface, pH goes up, we can lose a lot of ammonium into the air. Later on, as the ammonium nitrifies to nitrate and soils become anaerobic, then there's the opportunity for NO loss, N2O loss, which of course is what we're trying to target, one of the greenhouse gases, and some N2. N2 is inert, but it still represents a loss of very expensive fertilizer. And also, if you look at the bottom of the pipe, during excess rains, nitrate can go through the soil into lower depths beyond the root zone, or if it's systematically tile drained, we can lose nitrate through the tile drains into the system. At the end, the crops could only use the nitrogen that's left over after all these losses occur. So here, the next slide shows the concept of not only the pipes, but the valves. So the valves could be, as an example, adding a nitrification inhibitor. As we saw with the meta-analysis, we may be able to decrease N2O emissions with the addition of the nitrification inhibitor, which is symbolized by this valve. But we might be increasing the ammonium volatilization versus sort of a business as usual model. So what's left over in terms of the crop may not be that different because we've reduced one loss but increased ammonium. So the crop may not change in terms of value. Going one step further, if we look at urease inhibitors or incorporating the nitrogen, we can very effectively, as you'll see in some of the field slides, decrease ammonium loss at the expense of increasing N2O emissions and N2. Ammonium loss can be numerically a much higher loss than N2O, so the crop yields can increase, but it may be at the expense of N2O emissions, which of course we want to avoid. So ultimately, we want to look at multiple 4R practices, whether it be stacking maybe a dual inhibitor, urease and nitrification inhibitor, or incorporation with one of the inhibitors, using UAN instead of urea. And that way, try to look at reducing multiple losses, whether they are ammonium, N2O, N2, and so forth. And so to illustrate this in nitrate leaching, we have 3 corn plants to signify greater yields. Now, I work very closely with Ward Smith, and he provided this graph. And so this is sort of the process greenhouse gas modeling that's done with the NDC. And we had a modeling component in our pipe and valve paper. I've already talked about, the whole end cycle, so I'm not going to go over it here. But just to say that all those processes I talked about before, including, nitrogen assimilation, uptake by crops, mobilization, are modeled and taken care of with this denitrification decomposition model. So, and in the last, 10, 12 years in particular, 13 years, he has added many refinements to the model. Earlier on, adding a wheat submodel to it, and then trying to capture more closely the development stages of crops like corn and soybean. More recently, including more information about urea hydrolysis, soil pH influencing ammonium volatilization, soil hydrology and drain and tile drainage, which is a factor in many of our soils that are on flat clay texture soils. They are drained, and so forth. And in the last few years, doing a better job of trying to model and capture the urea hydrolysis rates and the influence of the inhibitors. So doing this model, again, we had a validation component. We took some field data. This is one of the more recent publications. And we could see here on this model, we're looking at more of the improved urea diffusion, hydrolysis, and looking at inhibitor efficiency. The old model were the blue lines, and whereas the black dots refer to the measured values. So you see, by looking at improved diffusion, hydrolysis, and so forth, the new model captures the losses much more carefully, whether it's broadcast urea with dual inhibitors, broadcast incorporated urea, or again, broadcast incorporated urea with dual inhibitors. So this was based upon a field study. When we get a very, from fair to good index agreement on the daily emissions, and Ward tells me that you can get even better improvement if it was done on a weekly or monthly basis, but that apparently is quite good for daily losses. And that was ammonium loss, and similarly N2O emissions. I won't go over all these graphs, but you could see very clearly that the red line does, for the most part, match the data very well with, very fair to good index of agreement when we looked at the modeling parameters. So again, we were looking at this pipe and valve model and want to simulate different sources, whether they include inhibitors, timing, whether we apply nitrogen at planting or maybe 4 weeks after, and we're using corn as the model crop, when it may be at the 5 or 6 leaf stage, looking at optimal placement, nitrogen rates, and in fact, even adding the soil health parameter, whether it's cover crops, crop rotation, or conservation tillage, and Diego will be talking about that in his presentation. And so I just want to go over, these are now DNVC modeled results and using 30 climate years. So it's looking at the average over all these years. And let me just take you through this graph. The next couple have the same format. In this case, we're looking at ammonium volatilization losses. And we're seeing that control, if you don't add any urea or any nitrogen, volatilization losses are quite low. In fact, I should say with this model, we're assuming there's always a background starter fertilizer, typically about 20 kilograms of N. So we do see a little bit of ammonium volatilization just through mineralization process stuff. But if we take the broadcast urea and let's look at that as the baseline. So we're seeing about 35 kilograms N lost using this model. It's even higher if we just add a nitrification inhibitor. So all the nitrogen is sort of kept in the ammonium stage before until a little bit longer with the nitrification inhibitor. And in fact, that if the pH goes up, can lead to higher losses. And this has also been reported in the literature. A urease inhibitor can indeed decrease ammonium losses. And I should have also added the black line is sort of our reference, the broadcast urea, but the 30% reduction target is the dashed line. So the first set of red treatments are what happens if we add all the nitrogen at planting. So whether it be broadcast urea, the first bar, or broadcast urea with the urease inhibitor, a nitrification inhibitor is the third bar. The fourth is broadcast urea with dual inhibitors. Compared to that is injecting UAN, injecting UAN with two inhibitors. So we could see that broadcast urea with urease inhibitor, broadcast urea with dual inhibitors, or injection clearly had dramatic reductions in ammonium loss. If we delay application to side dress or split it, we could see all the losses are lower, still fairly high with broadcast urea, with all the other treatments quite a bit lower, ranging upwards of 2 to 5 kilograms N. But if we then add conservation tillage to the mix, we can see very low emissions. So I'm going to take the same format, and again, on the upper right, you see our wind tunnels that we use to measure ammonium volatilization losses. We do that every day over 28 days to get our estimates. And the next, again, these are all modeling values using 30-year climates. Here's our control with nitrous oxide. In our region, the number of times it goes anaerobic, the high nitrogen input rates with corn, we do often see emissions, 5 or higher. In the last year, I was measuring some treatments, 9 kilograms of N2O per hectare. Broadcast urea is our baseline. And we see that the only treatment in this case that really reduced it with pre-plant treatment was the broadcast urea with a nitrification inhibitor, where we're able to decrease it below 30%, a little bit above with the dual inhibitors. And going a little bit further with the side dress treatment, also the dual inhibitors reduced it. But what's really interesting, if we have conservation tillage plus injection, we're stacking practices, we can achieve this target. And in fact, these are somewhat underestimates of how we can achieve. I'll show you in some slides, next few slides, how we have actually surpassed some of these emissions in field studies. And lastly, just the reactive N, without going through every single one, we could see that the injected treatments with the pre-plant, injected UAN or the dual inhibitors, same with the side dress, or looking at the combination of side dress and injection and conservation tillage, we're actually able to achieve a 70% reduction loss. And you can sort of see some of the field studies up in the right and some of the applicators we're using for side dress in the bottom right. So I've talked about some of the modeling work, and I'm just for the next probably 10 minutes or so, I'm going to show you some of the results from field studies. So here we're looking at nitrogen sources and placement, how they influence ammonium loss. This is when we started deploying wind tunnels to capture ammonium versus nitrogen, versus N2O, I should say. And we could see that if you look at this first paper that we published using these wind tunnels, this is just 1 year worth of data, and we have 40 kilograms of N lost, and we were applying at that time, I believe it was 150 kilograms. So it's almost, a quarter or so of the N was lost with broadcast urea. In that first set of studies, the super U, which is urea with both urease and dual inhibitors, we were able to dramatically reduce losses in this 1 year from 40 down to 10. If instead we just injected UAN instead of applying urea, so injecting it alone reduced it down to 10 from the 40, so that was a dramatic reduction. But we were able to actually virtually eliminate ammonium loss when we had UAN with the dual inhibitors, as you can see here. If you then looked at N2O emissions in the system, as has been reported in other studies, if we look at broadcast urea, in these years that we looked at it, we saw that the average loss was a little bit lower than we've seen more recently, about 1.7 kilograms per hectare with broadcast urea, 30% higher emissions with just the urease inhibitor. And part of that reason is that we've had more nitrogen in the soil. We've reduced the losses. More nitrogen's there. It's akin to adding more nitrogen fertilizer. So our N2O emissions went in the opposite way we want. Whereas with the addition of the dual inhibitor, urease and nitrification inhibitor, 12% decrease with broadcast and injection, same sort of pattern, a little bit lower losses, especially with the injected UAN. But you see the benefit of the dual inhibitors here. And in this first study, we also saw the dual inhibitors with broadcast urea increased corn yields by about 5%. They went up to from about 172 up to about 179 bushels per acre. But just applying nitrogen as broadcast treatment, from as injected versus broadcast, 10% yield increase and 18% yield increase, which certainly helped to make this sort of a profitable system from growers' perspective with those sort of yield increases. In our next study, we wanted to compare, okay, what happens if we add nitrogen all at once? So that's a pre-plant. It's usually done, the day of planting, just before planting, or at side dress. We also see that here we start, if you have control with no additional N above the starter, much lower losses, but of course our yields are about 50% lower as well. So pre-plant in this particular 3-year study, we're up to about 1.8 kilograms of N loss. Higher with just urease inhibitor, we have about a 30% reduction with pre-plant, the dual inhibitors. We also see a reduction by avoiding those early season losses, 28% reduction, still a little bit higher with the urease inhibitor, but we actually achieve a 34% reduction with the side dress plus our dual inhibitors. And we also see, if you look at corn grain yields, 14% higher yields with the side dress. So, encouraging farmers to delay application, add inhibitors, achieves both a N2O reduction effect plus a yield increase effects, which makes it worth their while. Third study, we're actually in phase 5, and I'm just going to talk about the third and fourth phases. Third stage was, okay, if you are going to add all your nitrogen up front, there's different ways of doing it. You can broadcast. You could broadcast and then work it in right after, usually within, the same day or within 24 hours, or you can inject. In our case, we worked, within a couple of hours, within an hour or so of application. We're seeing that, ammonium loss in this 3-year period, losing 22 kilograms by using the dual inhibitors. we had a 55% lower loss, very effective. If we incorporated without inhibitors, 34% reduction in ammonium loss, but we're getting even higher benefit with incorporation, broadcast incorporated, and with the inhibitors. Now we're only incorporating it really in the top 2 or 3 centimeters at most, whereas injecting it to about 7 centimeters, quite a dramatic reduction in loss, 98% in the case of injection with UAN. In that same study, we see that with the combination of inhibitors, we were able to get 13, 11, 9 bushels increase in yield, which sort of helps to incentivize the use of the inhibitors. Slightly better yields with broadcast incorporated than broadcast, and injection than broadcast, but that combination with the inhibitors and injection or broadcast incorporation certainly looks attractive. And sort of the last study that I wanted to cover is, okay, we know that injection works, but there's different ways of injecting. So here we're comparing broadcasting urea across the surface, which is attractive for a lot of producers because they could do it quickly. But some just add an injection slot in my upper right where you're injecting it about 7 centimeters. What we thought of is, okay, instead of a single injection shot, let's consider 2 injection slots, still adding the same amount of nitrogen, half the N in each slot. But what we are doing is we're decreasing the amount of N in each slot so that when urea hydrolyzes, the pH won't go up as much because there won't be as much urea hydrolyzing. And same thing with the nitrous oxide. The concentration of nitrate in each of these zones would be lower because they're split between two zones. We know that nitrous oxide loss is related to rate. So we're looking at how that would be effective. So, again, we measured ammonium losses, and they did occur, really right through that 28-day period. They weren't all at instantaneous or within the next first 2 or 3 days. It was a slower process, slower than what some of the literature implies. And I won't talk about these results specifically because I'll give you a summary one, but you can see how some treatments do consistently have higher losses than others. In this case was single injection UAN. But when we looked at a 2-year average, we were losing 13 kilograms Ven per hectare from broadcast urea, 72% reduction with the dual inhibitors. Going to single slot, so you're incorporating the soil, 23% reduction, but 97% single slot and inhibitors. Whereas just going from broadcast to the double slot, where half as much nitrogen is in each band, we have 65% reduction and 84% with the combination of double slot and injection. We also measured episodic N2O emissions, very low emissions we've observed before fertilizer application. A lot of the emissions occur afterwards, especially after high rain events. So this is just an example from 2020. And we looked at the cumulative emissions, and we see, fairly sizable treatment differences. And I'll show you the summary of those. So here we see broadcast urea having lower emissions. Part of that was because we've lost so much nitrogen from ammonium volatilization. There was less N in the soil to be lost as N2O. If in this case we use single slot UAN injection as the basis, with adding a urease inhibitor, it's about the same as a double slot, or a 16% reduction. But looking at double slot and UAN injection, we have a 53% reduction in loss. Higher losses in the years, there were wetter years, so we went from 7 down to about 3.5 kilograms N2O per hectare loss. And we saw that with this double slot injection, as you see in the far right, and this is the field picture in the upper right, we see, yield increases of, 7 to 13% compared to this broadcast urea. And lastly, we've also played with late application. A lot of farmers are interested in trying to apply nitrogen late in the season, whether it's wide drop or another way of surface application. You're limited. You really can't easily incorporate when you're applying it to corn that's at 10 to 12 leaf stage. In both years, applying fertilizer late in the season as urea, which is the upper graph, we're losing 55 to 58%. In fact, we're doing a great job of fertilizing the air, which of course we don't want to do because of all the respiratory issues, and ammonium is a precursor to PM 2.5. So we obviously want to avoid that. It's a loss of expensive N. But even with our best treatment, which is looking at UAN injection with the urease inhibitor, we're still seeing 15 and 21% loss. And I'm not showing it here, but when we compared corn yields, they were very responsive to late application, but they were responsive when we added the nitrogen more at the 5 or 6 leaf stage. So, looking at nitrogen management with cover crops, that's getting into that next phase where we're starting to say, okay, we know what works with conventional practices, but how do we manage nitrogen if we superimpose conservation tillage and we superimpose cover crops? And so in this last sort of phase, here we see ammonium losses with either no cover crop on top or a cereal rye cover crop in the bottom. The red is the urea line. Dark red is the urea with the 2 inhibitors, which is in particular lower with the cereal rye cover crop, and the green are with UA injection. And you can see again, it was a very dry year, so a lot of our losses only occurred when after the the granules were solubilized. In fact, some of the peaks occurred 14 days after application. And we also in 2022 had delayed urea hydrolysis, very little application, very, very dry soil conditions. Still saw fertilizer pellets, 10 days after application when I was out changing the traps. But when we did have rain, we saw higher emissions late in the season. And the 3-year average, in this case, had very high losses, ammonium volatilization over 50 kilograms per hectare loss out of 160 applied, 43% reduction with the inhibitor. Here we see injecting 95 to 100% loss. And both these first 4 treatments were without cover crop. The last 4 are with cover crop. With cover crop, we see the cover crop alone actually had a 19% lower loss. With the inhibitor, 63% lower loss. And we actually see net deposition occurring with the injected treatments. So very effective. So there's a cover crop effect, which seems to be additive in our particular study. Again, looking at N2O emissions, I'll just sort of skip by this one because of time constraints here. Same thing, this last year, we had very, very high losses, 2 kilograms per hectare, very lot of rain right after application, less rainfall, a lot of smaller events, and we can see those picked up throughout the growing season. And so ultimately we see lower losses with broadcast urea because we lost 50 kilograms or a third to ammonium volatilization. Higher N2O losses with injected, but we can decrease that with the dual inhibitors, the green bar, by 33%. Cover crops also help, and with the cover crop injected N, between 27 or 35% lower N2O emissions. And in fact, when you add the losses together, if you look at a systems approach, anywhere from 46 to 90% reduction in losses. So here is quite interesting. The first 4 bars are no cover crop. So we see a benefit of no cover crop with broadcast urea and the 2 inhibitors. probably about a 3% yield increase, 6% yield increase with injected UAN, and the combination of inhibitors, 16%. If we had broadcast urea, we actually see, and cover crop, as you see in the upper right, we see a huge yield penalty, 17% on average. Not quite as bad, but still a yield penalty. What's really interesting is that when we put the nitrogen 7 centimeters, 8 centimeters below, it's below that active decomposition layer where that cereal rye is decomposing. The microbes don't have as easy access to it. Crop roots do. So we've overcome this yield penalty with injecting UAN in presence of a cover crop. So I'm coming to the end. My point here is that nutrient management can give us a lot of tools or valves that can be used in order to regulate and help reduce N losses from the system. You can't just look at each loss in isolation. You have to look at the whole system. Conservation ag piece can also help achieve these objectives. And ultimately, we have found in general sort of take-home points. Side dress application can allow us to avoid early season N2 emissions, typically 3 or 4 weeks after planting. The dual inhibitors can reduce both ammonium and NO emissions, and in many cases increase crop yields. The improved placement, in particular dual injection system, helps to reduce urea concentration, which reduces losses, increases nitrogen availability and crop yields. And the example I provided was conservation ag and cover crops can also improve cell carbon, which I didn't talk about, but we are seeing some benefits. And diverse rotations can be beneficial, and how they help reduce losses. And this conservation ag pieces will be covered by Diego. We'll appreciate all the funders, the grower groups, fertilizer industry, Foundation Food and Ag Research, Ag Canada, for supporting this research. And that will end my part of the presentation. And I'll turn it over to Hiro and to introduce Diego. And thanks for your time.
Thank you very much for the very informative presentation. Our next speaker is Dr. Diego Abuelos. He is a senior researcher at Aarhus University Department of Agroecology, Denmark. His ambition is to reduce greenhouse gas emission and improve nutrient cycling in agroecosystem while maintaining optimum production level under current and future climate conditions. His research group combines empirical and modeling approaches to design efficient and diversified cropping systems, pointing the way for the sustainable management of the land and its nutrient cycles. Diego is an associate editor of Geoderma and Agronomy for Sustainable Development, and a member of the editorial board of Agriculture, Ecosystem and Environment. He is currently leading several national and international projects funded by public and private donors. And with that, I'll turn it over to you, Diego. Thanks.
Thanks. Okay, let me start sharing the screen.
Yes.
Okay, let's see. And this
Yeah.
This is not correct, right?
Correct. Just.
Yeah, you would need to swap the view.
Yeah.
I think
So
from the display settings. Yeah.
Like this?
Okay.
Excellent.
Yes.
Okay. This down. Yes, okay. So thanks a lot, Hero, and also Tista and Craig, for the opportunity to present some of these results, what we have been doing lately regarding this topic. It's a great opportunity, and I'm happy to spend the next 30 minutes more or less talking about primarily about this article, the role of conservation agricultural practices in mitigating N2O emissions. So this is a study that we conducted under the umbrella of the GRA, the Global Research Alliance, in particular as part of the Conservation Agricultural Network. So that's why I got involved in this, and Craig invited me to be part of this. But I'm using this opportunity also to talk about two other studies that I think that will be interesting for the people attending the webinar today. The first one is this one, about predicting field N2O emissions from crop residues based on the biochemical composition. This study has received a lot of attention from policymakers and scientists lately, because the findings are being used to develop tier 2 approaches in several countries to account for N2O emissions from crop residues. It's highly applicable. And then I would also like to talk about this second order meta-analysis that we published a couple of years ago, synthesizing the evidence of nitrous oxide mitigation practices in agroecosystems, again, because it gives a wider overview of the potential actions that we can use to reduce N2O emissions. And then finally, I will emphasize the need for process-based modeling at landscape and regional level in order to achieve successful N2O mitigation, to incentivize farmers and to give a tool for policymakers to give the right decisions regarding N2O mitigation strategies, and the need to go beyond field scale for effective greenhouse gas mitigation, which means that we need to consider not only the field, which is what we normally do, what I normally do, and I know that Craig as well, and many others, but there are other components of the agri-food chain that we are overlooking that are really important. And I will use this opportunity to mention just some of them very briefly. I'm not going to define what conservation agriculture is, because most people in the audience knows this already, but just briefly, the main principles are to promote permanent soil cover, for example, with cover crops or crop residue retention in soil surface, crop diversification with, for example, different crops in rotation, and minimum soil disturbance with no tillage or reduced tillage. And the main goal of these principles, of these practices, is to promote soil and water conservation, reduce management and labor, increase soil carbon storage. So right away, there is a climate benefit from these practices. And there are many other ecosystem services that are promoted by these practices: increase soil microbial diversity, soil macrofauna diversity, pollinators, a lot of benefits associated with these practices. What it is not well known is the impact that these practices may have on N2O emissions, and that is exactly what we try to investigate in this meta-analysis. The treatments were cover crops compared to no cover crops, diversified crop rotations compared to monocropping, and no tillage, reduced tillage compared to conventional tillage. So we collected all of the available information from field studies. We were quite restrictive in that way, all including realistic field studies, investigating impacts of these strategies on N2O emissions. We also extracted auxiliary information from all of the studies: climate variables, soil properties, location, and many management practices of relevance for N2O emissions. And once we finished the databases, we meta-analyzed them using the tools that you could see here. So for the effect size, we use the natural log transform response ratio. We then proceeded with a weighted mixed effects model using the metaphor package in R. And to identify the most important predictors of each of these practices, of the effect of each of these practices on N2O, we used a random forest model selection approach. You can see here the geographic distribution of the studies that were part of the database. So for the final databases included 97 direct comparisons from 19 studies for cover crops, 33 comparisons from 12 studies for diversified crop rotations, and 151 comparisons from 42 studies for no tillage and reduced tillage. There were several observations from the United States and from Canada, from Europe and China, and no observations from Africa, for example, which is unfortunately a bias that affects this type of research pretty much always. Although the number of data sets is increasing, but we very often don't, that region is underrepresented, unfortunately. But overall, we could say that the geographic representation of the studies included in the database is quite okay. So these are the main findings. You can see on the left what we found, and that is that no tillets reduced tillets in blue, significantly decreased N2 emissions by 11% on average. In contrast, the other two practices, diversified crop rotations and cover crops, had no significant effect on N2 emissions due to the very large variability across the study sites. This basically means that, as you can see, these practices sometimes increase N2 emissions, sometimes decrease them. So very variable effects. On the right panel, you can see that the responses of soil N2 emissions were normally distributed for cover crops and for no tillets, reduced tillets, but they were not normally distributed for diversified crop rotations due to the lower availability of observations in SIMS. Our random metaforest approach identified soil pH, soil total nitrogen, and soil organic carbon, so the three variables in red, pink, whatever that color is on top. These were the most important predictors of the effects of cover crops on N2 emissions. I'm only going to talk about the first one for the sake of, sticking to the allocated time. What we could see on the first regression, the first panel of soil pH, is that cover crops are more likely to reduce N2 emissions at neutral soil pH, so around 7. That is probably because at neutral soil pH, cover crops simply grow better. It's the soil pH that favors crop growth and microbial growth in general, bacterial. And by increasing cover crop growth, it allowed the crop to retain more nitrogen in their biomass and therefore reduce the availability of soil mineral nitrogen for nitrifiers and denitrifiers. And it also increases transpiration, evapotranspiration in total, which reduces the soil moisture content below the optimum for the nitrifiers. That's the most likely explanation for that relationship between the effect of cover crops and soil pH. For diversified crop rotations, among the 11 predictors, mean annual temperature, that's the first one, soil pH and clay were the most important predictors. We could see that diversified crop rotations are more likely to reduce N2O in cold climates, basically, when the mean annual temperature is around 5, 7. It's not easy to know why, but it might be due to the specific crops used in these climates, in these regions, to diversify the crop rotations. For no tillets and reduced tillets, the most important predictors were soil organic carbon, mean annual precipitation, and the soil CN ratio. We could see that it was more likely to achieve a reduction in N2O when no tillets and reduced tillets is practiced in soils that have a very low soil organic carbon prior to the adoption of no tillets and reduced tillets. This can be, we know that increasing soil tillets can increase soil organic matter content, and increasing soil organic matter content can improve soil structure, which suppresses the formation of anaerobic microcytes in the soil. And those are the ones that trigger N2O production from denitrification. And of course, it is more likely to achieve these increases in soil organic carbon and in soil organic matter in soils that have a low organic carbon content at the beginning than in soils that already have a high organic carbon content. In terms of management, cover crops tended to increase N2 emissions mainly during the cover crop phase of the rotation, you see that here, which could be explained by the carbon supply from rhizodeposition through actively growing root systems promoting denitrification. We also found that the capacity of cover crops to reduce N2O emissions increased as the end fertilizer rate to the previous cash crop increased, and this is something to be expected because there will be more nitrogen, residual nitrogen after the cash crop phase for the cover crop to immobilize and therefore to have a stronger effect on N2O emissions. We also found that there was no difference between legume and no-legume cover crops in terms of N2O, which contradicts several other meta-analyses. But what our results show is that legumes have the capacity to self-regulate nitrogen fixation. So if there is high nitrogen available in the soil, they reduce the amount of nitrogen they fix from the atmosphere. And in that sense, they behave like any other, like a grass or a forb, in terms of acquiring nitrogen from the soil. So they are highly beneficial for reducing N2O. For diversified crop rotations, this is a broad category, diversified crop rotations that involve a mixture of different agronomic practices related to each of the crops in the rotation, and the effects on N2O may depend on what crops are used to diversify, the fertilization of each of those crops, and the tillage practices required for each of those crops. So it's a really broad category. But it could be argued that in many diversified rotations, the total N2O emissions from the entire rotation sequence can be lower, just because there are fewer phases that receive mineral fertilizer, right? However, we did not find this effect. We could see that the emissions were the same over the entire rotation of 4 or 5 years, or when we were only comparing, say, maize in a diversified rotation versus maize in a monocropping system. And for no tillage, reduced tillage, we can see that N2O reductions were more common in humid climate, which has been also shown in previous meta-analysis, and gives us an idea of where to implement these practices from an N2O mitigation perspective. So the conclusions, implications of the study were that conservation agriculture can promote ecosystem multifunctionality, that we know, but the climate benefits in terms of increasing soil carbon storage are not always realized, because sometimes certain practices can increase N2O emissions under specific edaphotic conditions. We reduced N2O emissions. However, sometimes nutrients can have yield penalties, especially under wet and cool soil conditions. And in these conditions, perhaps zone or strip tillage may represent a better option. And we could see that the variation in the response of N2O emissions to cover crops and diversified crop rotations was relatively well captured by specific soil and climatic factors, the ones I just mentioned. And therefore, these results provide a roadmap of the regions of the world in which conservation agricultural practices can mitigate climate change more efficiently, both increasing carbon and reducing N2O. In this second study that I want to talk about today, I'm doing okay in terms of time.
Yes.
Here, we conducted a meta-analysis to understand the main biochemical properties of crop residues driving their effects on N2O emissions. And we found that on average, very broad average, crop residue removal crop residues can increase N2O emissions by 44% compared to removing the residues from the field. But we also find that crop residues could either increase or decrease N2O emissions depending on the biochemical composition of the residue. The main predictors of these effects were the easily degradable water-soluble carbon, cellulose, and the amount of nitrogen returned with the crop residue. So you could see in this PCA the response rate of N2O, that's the LNRR N2O, those are the N2O emissions. And the residue, nitrogen return, water-soluble carbon, that's WSC, and the soluble fraction, those are the ones positively related to the amount of N2O, and negatively related would have the CN ratio of cellulose, for example. And since these biochemical properties were strongly correlated with each other across all the different crop residue types, we were able to develop a simplified classification for crop residues based on the maturity stage, as you can see. And according to this maturity criteria, immature residues strongly stimulate N2O emissions, while mature residues have marginal effects on N2O. And what we can derive from these results is that it is possible to make a very simple differentiation in the emission factor for mature and immature residues, which could be a good solution to better account for this source of emissions following a tier 2 approach in national inventories. Of course, we need further research to clarify this criteria is applicable in most countries across the world, but it is a starting point that seems to be quite robust, and it provides an opportunity to refine and improve national inventories. Then the third study I want to talk about is the second order meta-analysis led by Diego Grados. We know that there are several agricultural practices that can reduce N2 emissions. There's been research on N2O from we are in 24. It's been 70 years since this field began. But what we still don't know is the overall mean potential of those practices and how variable that potential can be in relation to each other. And this is important information for several things as well. To address this knowledge gap, last year, 2 years ago, I don't remember, we conducted a second order meta-analysis, which is basically a meta-analysis of meta-analysis, to assess the mitigation efficiency of the most common N2O mitigation practices in agriculture. We used 27 meta-analyses, including 41 effect sizes based on 1,119 primary studies. And these are the main results. As you can see, the variability is very large, which implies that we need to understand better the conditions that favor the potential N2O reductions achieved with each of these practices, so aligning with the previous results. And this variability is particularly high for cover crops and for diversified crop rotations, so the two practices that I mentioned, that I talked about earlier. But let me simplify this figure a little, because I think it is more convenient to, your eyes will go faster to the main results if I do it like this. So what we found is that technology-driven solutions, that is enhanced efficiency fertilizers, drip irrigation, biochar, and optimization of fertilizer use, have a very high mitigation potential. Conversely, more agroecological practices such as organic fertilizers or cover crops may increase N2 emissions and only lead to reductions under certain soil and climatic conditions. Of course, they have many other benefits, but focusing on N2O, the results are more uncertain. The consistent mitigation observed with the technological solutions has very important implications. For example, we should try to incorporate many of these practices into process-based models, because currently they are not well represented in most of the available models, and many policy decisions related to greenhouse gas emissions are based on the use of models or tier 3 approaches. Another implication of these results is that we need specific emission factors for these mitigation practices, so we can have better national inventories again with tier 2 methodologies, and also to have a tool to reward farmers when they implement beneficial management practices. A few things to consider based on this study. There are several policies and regulations trying to achieve climate neutrality. These have been launched over the last years all across the world. And considering that the overall range of N2O mitigation potential for the technology-driven solutions that we found is 30 to 50%, our study indicates that adopting a portfolio, not one, but a range of strategies for N2O mitigation is crucial, and it may contribute decisively to achieving the mitigation targets. One of the reasons limiting the adoption of mitigation practices very often is that policymakers and farmers tend to believe that there will be a trade-off between crop production and climate change mitigation. So they will impose this practice and that will have a penalty in our yield. But that is not true at all. Several N2O mitigation practices do not compromise yields. In fact, many of them increase crop yields or tend to increase crop yields. Examples are biochar, mainly in tropical regions, or deep fertilization, drip irrigation, optimization of fertilizer rate, increased frequency of fertilizer application, liming, nitrification inhibitors, urease inhibitors, and the combined use of inhibitors. All these tend to increase yield, not to reduce it, which means that efforts to reduce N2O emissions from agricultural soils are likely to simultaneously increase crop productivity, not decrease it. Since our study, this second order meta-analysis, also involved a systematic review of the available scientific literature, we were able to identify research areas that deserve further attention in future studies. An obvious one are the interactions between mitigation measures, because we could evaluate them individually, but there's not a lot of research combining mitigation measures. It is difficult to evaluate, of course, these combinations, but they may be the key to achieve the next level of mitigation when there are synergies between them. And other novel strategies to investigate are intercropping, the release of biological nitrification and nitrification inhibitors from certain plants, silicate additions, inoculants for legumes, and more recently, non-denitrifying N2O respiring bacteria with organic waste as a substrate vector. This is from the recent work of the group of Lasbakken in Norway, published in Nature like a few weeks ago. So, okay, what should we do based on these findings? We should try to incorporate N2O mitigation practices into process-based models. This is key because they are not well represented. We need to develop specific emission factors for these mitigation practices for national inventories based on Tier 2 approaches. We need to reduce greenhouse gas emissions from agriculture, that is N2O and methane from rice paddies, while promoting soil carbon sequestration. Otherwise, climate neutrality is just a joke. We need both agroecological and technology-driven solutions, as long as they do not compromise food security. One of those will not solve the problem. We need both of them. And we need to speed up the adoption of available mitigation strategies now, while continue developing more efficient strategies. So climate change is here, and we need to act now, and we need to be effective. While we get better things, we still need to implement the tools that we have at our disposal nowadays. And just regarding to some of the things that we're doing now, for example, in Denmark, we are currently trying to develop a Tier 3 approach for national inventories to account for N2O emissions from Danish soils. And this is the type of, this is Denmark, for those of you who don't know. This is the type of resolution that we can already achieve. And so we're going down to, I believe it's 30 meters, 30 by 30 meters. And this is a large project that is just at the initial stages. And here we have representatives from the ministries and from the authorities and the people involved in the national reporting for the inventories to the United Nations. And we have a wide range of scientists, and we have representatives from the farmers union. So we are trying all to get together in order to find the best way to account for N2O emissions, to account for strategies to reduce N2O emissions, and to monitor them, to verify them, and to actually achieve substantial N2O mitigation at the national level. This is just, of course, you can see the results, but everything that is behind these results needs to be improved. All the representation of nitrification and denitrification processes, the activity data that we use to run these models at this scale, doing something that is representative for all of the farms of Denmark. So there's a lot of work still left to be conducted, but we are already having promising results. The next stage is to bring it to the EU scale. So we are developing some proposals, and likely, hopefully, we will be able to get some additional funding to bring this to the next level and develop pool nitrogen budgets for the EU, the entire EU. This is an ambition that we have. And again, we are doing this mainly with Landscape DNDC and with Thyssen, and among others, we are collaborating with researchers from Colorado State University, Stephen Rosso, Frank Guru, and many others. And last but not least, this is my last slide. Most of the discussions we normally have are focused on what happens at the field farm scale, which is just what I just presented, what you can see in this slide. And that is, of course, very important. But we often overlook several very important drivers of nitrogen cycling in the agri-food system. For example, consumers. So each and every single one of us can be the most important determinants of the agricultural landscape through our food choices. The agricultural industry as well is another key player. Obviously, fertilizer companies, that's an obvious one for N2O, but also the ones involved in biorefining, pyrolysis plants, food manufacturing, food loss and food waste, all of them have a big role to play in terms of climate change mitigation from the agri-food sector. And last but not least, the entire land use change and forestry sector is vital if we really want to follow where the big changes in greenhouse gas emissions can happen. A major advantage of models is that they can cover multiple spatial scales and they can cover all these multiple interactive components of the agri-food system, from field production to consumer choices. We need to integrate all of these components in modeling and assessment frameworks to consider all these loops and feedbacks and to reconcile and coordinate the views of scientists, policymakers, stakeholders, and the civil society if we want to achieve the mitigation targets. And of course, reducing into emissions will be a key element of that journey towards climate neutrality. And I hope that the work that we are conducting now with modeling can be a framework to be adopted in other countries so we can implement all the mitigation strategies that we have been investigating for so many decades. And with that, I conclude my presentation.
Thank you very much for the informative presentation. We have few questions for you. First, Craig, there is a question about why combine NI and UI reduce the ammonia losses, and why does UI become more effective on the presence of nitrogen?
Okay, so so the urease inhibitor, of course, targets urease enzyme and slows the process down, and with the hope that rain and that urea will diffuse, rain will bring it in the soil, sort of move it into the soil, especially if it is on the surface, and that should help to slow down the increase in pH and so forth. Now, in fact, I may have misspoke, but the dual inhibitors, urease inhibitor alone will in fact decrease ammonium loss more than the dual inhibitors. Problem is, urease inhibitor on its own has very little impact on N2O emissions. So that's why we've been sort of encouraging the use of both, and that to get that sweet spot so where both the urease can keep the ammonium losses down and the N2O losses are reduced with the nitrification inhibitor. So yeah, the combined gives you both of those. Urease alone can be more effective for ammonium, but not very effective at all, or in fact can increase N2O in some cases.
The other question, partially you answered, I think. What are the consequences of the environment of ammonia volatilization? Is it only loss of nitrogen?
Yeah, so certainly it is an expensive loss of nitrogen if it goes up the air, but there's multiple consequences of ammonium in the air. So the ammonium can react with sulfur dioxide, it can react with nitrogen oxides and form PM 2.5, which is 2.5 micron particulate matter. So the higher level of PM 2.5, it's smog, sort of more common term, and it's an air quality issue. In particular, people with respiratory issues have higher challenges with breathing, with high smog levels, infants as well. So yes, quite clearly from a health perspective, that's an impact. And the other thing is some of the ammonium that's lost can redeposit elsewhere and maybe an environment that you don't want the ammonium to occur. So there's sort of environmental and health issues associated with ammonium loss as well, above and beyond the fertilizer value.
Also, just it seems a related question. Is that mean the nitrous oxide are denitrification source? If this is the case, does applying Ni reduces the emission? Of course, it does.
So why does UI increase N2O emissions? So what's happening there is that, and we've seen it in several field studies, where also our models predict increased emissions as well. And what's happening is that urea hydrolysis goes urea with the urease inhibitor, converts urea to ammonium. But if the pH goes up, ammonia is lost. Catch is if you have let me just look at this question again. So
Actually,
if you, where is it now? So yeah.
We took it off.
Okay. Yeah, it's just sort of looking for
It's in the answered section. If you look at if you see the tab answered.
Yeah. So what happens is if you have just a urease inhibitor alone, what happens is, yes, you can reduce losses, and we've measured in multiple studies up to 50 kilograms or a third of the nitrogen. In fact, in 1 year, I measured N2O loss or ammonia losses that were 2/3 of the N applied. So if you have really high losses and you have just a urease inhibitor, it's like adding, so you've saved that nitrogen from being lost. So there's more nitrogen in the system. So N2O emissions can go up because it's like adding more fertilizer. That's why urease inhibitor on its own, because it keeps more nitrogen in the soil, if it does become anaerobic, you have higher N2O losses. But if you have a urease inhibitor and nitrification inhibitor, the urease inhibitor can keep ammonium losses down, but the nitrification inhibitor will slow the nitrification process and could also help to decrease N2O emissions at the same time. So that combination is really critical.
Thank you. Next question is, are farmers willing to inject or do conservation tillage? Which one is better than the other?
I was actually involved in a webinar earlier in the week, and it was a smaller group of farmers in our area, well, in Ontario. And in fact, that group, which are probably the more innovative ones, over 20% of them were already injecting. More were either broadcasting or broadcast corporate. So yes, there is a group that will inject. We'd like to see that a little bit higher, especially from the ammonium loss perspective and for the crop yield perspective. So yes, there are farmers doing that. So no-till became very popular back probably the sort of 80s and 90s. And it does work extremely well in dryland areas like the prairies. It works on sort of coarser texture soils or loam soils. But sometimes on these flat clay soils or clay loam soils, especially in central Canada, some of the northern US areas, and other places around the world, if you have no-till alone, then what happens is the soil can become wetter if you have a wet spring, and soil can be a bit cooler. So in those cases, emergence may be delayed with no-till, and which could impact yields. So in situations where you do have wet springs, when you do have waterlogged conditions early in, because you're clay soils, you might want to consider a compromise. So more of a conservation tillage system in those particular cases. And, the example that we've used in our field studies and Diego gave in his presentation, using something like zone till. So in that case, what you're doing, it's sort of the best of both worlds. you're cultivating a very narrow zone, typically about 20 centimeters. Whereas if it's corn 76.2 centimeters between row, only 28% of the area is cultivated. And then you plant, especially with precision planters, an auto steer, you could plant in the center of those zones. So you have that great seed bed for early emergence, especially in these clay soils that are in wet environments. So you have better emergence, yields that are comparable to those of conventional till, but you have the benefits of no-till between those corn rows because carbon breakdown has reduced. And in fact, in one study that I was involved with a colleague, Shuming Yang, where we have long-term conventional till, no-till, and zone till, our zone till treatments had 12% higher carbon. This was after, I can't remember how many years, but it was over 10 years. Because of that reason, it's like a bank account. We've kept the yields higher with the zone till, higher than the no-till, and especially in those wet years. So carbon inputs have been high, but the decomposition in zone till is a lot lower because you're really pushing the residue aside and have most of the area zone till. So the net benefit is carbon losses through CO2 were lower, carbon inputs were higher, and carbon was starting to build up. So in those situations where no-till doesn't work, then something like zone till or some conservation tillage might be an option. Sorry, that was a long-winded answer to the question.
Well,
But it was
there
good
is
one.
another good.
Good question.
Also, yeah, I think there is. I'll continue with that. It seems the next question, I'll skip Diego one and go to, do you have indication on how the presence or absence of mulch influence the effect of conservation agriculture on nitrous oxide emission? I think you alluded just now into that a little bit.
Yeah, so I'll start with that, and then Diego will, who I'm sure has worked with that as well in his paper.
Yes.
So in our cover crop system, in fact, we actually had lower N2O emissions just with the cover crop alone, and so we've sort of seen some benefit, and certainly even with sort of mulches from that. I'll defer to Diego because I know he's looked at it with the meta-analysis in more depth. So if you want to take over, Diego.
Yeah, sure. So it's a good question, and a complex one as well, because we conducted a parallel meta-analysis trying to see the specific management practices with crop residues and how would they affect N2O emissions. And then our expectation was that the mulches, so having the crop residues on top rather than incorporated, would increase N2O emissions further. They can actually be like a hotspot for N2O emissions because then there's lower immobilization, which can reduce N2O emissions. There's higher water retention in the crop residue, which increases denitrification of the soil surface layer. So we were expecting higher N2O emissions with the mulches, but we didn't. So it seems to indicate that there's, again, large variation depending on soil and climatic conditions. So everything happening with the crop residues is tricky because it's really, it goes from large increases to very large decreases. If there's a strong immobilization, N2O emissions can be actually strongly decreased by crop residues. So in principle, there is an interaction and mulching would increase N2O emissions, but it's not always found in field studies, not all.
Also, can you?
And again, if I could just add, that's why, especially if there's that active layer and that higher carbon with mulches, sometimes if you can inject and put it a little bit below that air, that high concentration with the mulches, you might be able to overcome it, or at least that's what we've seen with sort of cover crop systems.
This one is for Diego again. It's how you could explain one more time the response by fertilizer rate.
I guess that refers to when I was talking about the effect of cover crops on N2 emissions, and there was a relationship. That effect was dependent on the end fertilizer rate applied to the previous cash crop. I think that's what the question is referring to. And what we found is that the higher the nitrogen application rate to the cash crop, the larger the potential of the cover crop to reduce N2 emissions. And that could be because the amount of residual nitrogen after the cash crop is greater, which means that the cover crop can retain that nitrogen in its biomass and therefore reduce the availability of soil mineral nitrogen for N2O producing processes. If, on the contrary, the application rate for previous, say, corn, maize, is well adjusted to the needs of the crop and for the supply of nitrogen from organic sources throughout the growing season, then there will not be any nitrogen left to be retained by the cover crop. So there's very little scope to reduce N2 emissions for the cover crop.
Next is for Craig again. Did you ever reduce nitrogen application rate with the use of EEFs? And do you think you could reduce nitrogen application rate and maintain yield with the control?
Yes, we did, and we haven't published that yet. But in one of our studies where we looked at different enhanced efficiency fertilizers, including ureas and nitrification inhibitors, placement, whether it's surface versus injected. We also had a series of treatments at different rates. And we found, again, we're still working up this data and hope to get it out in the next few months. But yeah, with some of our treatments, we can decrease the rate if we use the enhanced efficiency fertilizer. We can reduce the rate and still achieve the same yield goal. So we have looked at that, but unfortunately haven't yet had time to publish that, but it's one of our next ones coming up.
Okay. Well, thank you. I think we are getting close to our time limit. Just one more question. Maybe the rest we will answer via email or put it on the website on the GRA. The last question is, how common is dual slot fertilizer application?
Right now, not too common yet, although I was at a farm show a couple of years ago, and there were a couple of equipment manufacturers that were introducing it. And I'm hoping as we present more of the results, that will be taken up. But it is a fairly new practice. There is a higher upfront cost because you have a little bit more equipment. But if you can increase yields and decrease emissions, it may pay for itself over the long haul.
Well, thank you very much for answering these questions. And we will give you some time to answer the rest, maybe. I would like to thank you, our presenters, for the very informative presentation, and the GRA and our coordinators, she is the one running the show for us, and everyone for your interest and questions. And we hope you have a nice evening or rest of the day. Thank you very much and appreciate your interest, and we will answer your question as we can. Thank you.
Bye
Thank
now.
you.
Thank you.
So, it's been a pleasure.
Thanks, everyone. Thanks, Sarah.